Swayam Prabha. Digital India. Educated India.
Welcome to Basics of Noise and its Measurement. My name is Nachiketa Tiwari. This is week 1, and what you are going to listen to is the 5th lecture of this week. Today, what we are going to talk about are some of the principal terms, some of the key terminology which is used in the area of acoustics and noise and its measurement. So let's look at some of these terms. So what we'll talk about are all of these terms: decibels, octaves, decades, bandwidth, wave number, tones, noise, and noise is of two types, pink noise and white noise. And then weighting, I have put it here, but probably I will not talk about it today. We will definitely cover weighting, but it will happen maybe a little later in the course. But decibels, octaves, decades, bandwidth, wave number, tones, pink noise, white noise, these are some of the terms which we'll definitely learn what in terms of what they mean in today's lecture. So, tones, what is a tone? When I say 500 hertz tone, what it means is that I have generated a sound wave. The shape of the sound wave along, if I plot it in as a function, if I plot the pressure as a function of time, is a sinusoidal function. So a tone is a sinusoidally shaped pressure wave as a function of time. So if I say that it's a 500 hertz sine wave, then it means that so 500 hertz tone it means that pressure is nothing but some amplitude sine 2 pi ft plus some phase, and this value is 500 hertz. So that for that reason this is known as a 500 hertz tone. So I can have a 500 hertz tone, 20,000 hertz tone, 1000 hertz tone, and whatever. So that is what a tone is. The next term is an octave. So what is an octave? So octave is the interval between two sound pitches or two tones which are separated by a factor of 2. So what does that mean? So you have an octave. Okay. So I can say 20 to 40 hertz. This is an octave. Why is it an octave? Because the ratio of this 40 over 20 is 2. So that's why it's an octave. Now why do we actually call it as something octave, OCT? Because typically OCT corresponds to the notion of 8 that we will see later. But if the ratio of the upper, so suppose there is a band in which sound is being produced, and there's an upper limit of that band, there's a lower limit of the band, and if the ratio of these two frequencies is 2, then it's an octave. Another example of an octave, 40 to 80 hertz. Another example of an octave, 80 to 160 hertz. Another example of an octave, 22.5 to 45 hertz. So as long as this F2 and F1, if the ratio of F2 over F1 is equal to 2, then that band of sound is known as an octave. Similarly, this terminology is used because of some historic reasons. But once the SI system came into picture, then people also introduced a term known as a decade. So some examples of decades: 2 to 20 hertz. F1 is equal to, or 10 F1 is equal to F2. This is F2, this is F1, so 2 to 20 hertz. Okay. Another example of decade: 20 to 200 hertz. This is again a decade. So all the frequencies lying in between 20 to 200 hertz belong to this particular decade, 20 to 200 hertz decade. So octave, in case of an octave, the ratio of upper frequency limit and lower frequency limit is 2. In case of a decade, the ratio is 10. In most of the engineering literature, octaves are more popular compared to decade. But regardless, when we plot the frequencies on a logarithmic scale, either we plot on the x-axis octaves or we plot on the x-axis decades. But so the only difference between these two is the ratio of two frequencies, upper and lower bandwidths, lower limits of the band. So that is what a tone is, and that's what an octave is. Now I wanted to give you a historic perspective as to where this number comes from. So in Western classical music and in Indian classical music, we have these 7 notes. In Hindustani classical or Carnatic classical music, we have the sa, re, ga, ma, pa, dha, ni, sa. So sa, re, ga, ma, pa, dha, ni. These are 7 notes, and then you go to the next level, and that is sa again. So there are 8 notes, total of 8 notes when the cycle of the whole thing starts again. Similarly, in Western classical music, you start with C, D, E, F, G, A, B. So these are 7 notes, and then you go to the 8th note, and then again you start with another C or another sa. So because the 8th note starts with another sa, that is why this entire, and the ratio of the lower sa, in this case let's say it's 240 hertz, and then you keep on going down, and then the next sa which comes, or next C which comes, is 480 hertz. So because the ratio of these two frequencies historically was set at 2, both on the Indian side as well as on the Western side, so that's why it was known as octave. So octave was a band of a frequency bandwidth in which the upper limit and the lower limit was 2, but there were 8 notes in between, 8 notes in between. So that is what is the historic perspective. So in octave in Western classical music and an octave in Indian classical music, the ratio of the frequencies was 2, but there was 7 intermediate notes, and the 8th note was again a repetition, but in the next octave. Now, in that context, I also wanted to bring to your notice some information about intermediate frequencies. And first we will look at the Western classical system, and then we will go to the Indian classical system. So in Western classical system, you start with C, note C, which corresponds to sa in Hindustani. Then you go to D, which corresponds to sa, re in Indian system. Then you go to E, which corresponds to ga, and so on and so forth. And if you look at the ratio of the frequencies here, and then between C and D you have a C sharp or a D flat. Between D and E you have a D sharp or an E flat. And then between E and F you don't have an intermediate frequency. But between F and G you have a F sharp or a G flat, and so on and so forth. And then when you look at the ratios of adjacent frequencies between C and C sharp, it's 1.0595. Between C sharp and D, it's again 1.0595, and so on and so forth. And if you multiply all these factors, 1.0595, ones, two, three, we multiply these by itself, the required number of times, essentially you will get a factor of 2. And that factor of 2 corresponds to the frequency, the ratio of frequency of the lower C and the higher C. And because these ratios are constant and they are set at 1.0595, this scale of notes which is used in Western classical music, which spans over C, D, E, F, G, A, B, and then starts with another C. This scale of notes is known as equally tempered scale, because these notes are in geometric progression and they get multiplied, their frequencies get multiplied by 1.0595 successively. So that's what an octave means in a Western classical music, and that's how we have borrowed that term octave into scientific language. So the next thing we look at is the Indian classical music. And in Indian classical music, these notes are known as shrutis, and the whole scale is known as a sargam. So the basic note is known as sa, and sa is an abbreviation for this note called shadaj. Then you have re, which is an abbreviation for rishabh. Then we have ga, which is gandhar, ma, madhyam, pa, pancham, dha, dhavat, ni, nishad, and then you have the next sa, which is in the next level. Okay. Now, in Western classical music, these ratios were set at 1.0595, and they were also intermediate frequencies. C sharp or D flat, D sharp or V flat, E sharp or G flat, and so on and so forth. Similarly, between Shadaj and Rishabh, there are intermediate frequencies. Rishabh and Gandhar, there are intermediate frequencies, and so on and so forth. So that much is similar between how notes are organized in Western and Indian classical systems. But a key difference between these two systems is that in Indian classical system, the ratio of frequency of the lower sa and the higher sa is 2, but the ratio between adjacent frequencies is not set at 1.0595, but it is set at a level which is most pleasing to the ear. So in Western classical music, you have ratios which are 1.0595 and they are determined mathematically, but there is no reason why they have to sound good or bad, but they are mathematically determined because that is how they figured it out. But in Western Indian system, they didn't use a rigid mathematical formula for going to successive frequencies, but they said that okay, all the intermediate frequencies will be tuning them at specific values such that they sound most pleasant to our ears. So that is how they figured out all the intermediate frequencies, but they made sure that between one sa and the next level sa, the ratio was preserved at 2. So because this particular scale on the Indian side, it does justice to our ears, it is known as just tempered scale. And the Western classical music is known as equally tempered scale because the ratios of adjacent frequencies are equal. So you have a just tempered scale and an equally tempered, just tempered scale in case of Indian music and equally tempered scale in case of Western classical music. So that is what I wanted to talk about octaves and decades. Now it just turns out that theoretically I can have one particular frequency and just 2 times it, that will be an octave. So I can have 1 hertz to 2 hertz, that is an octave, and also it could be 1.5 hertz to 3 hertz, that's also an octave. But then when we report literature, when we report results in standard formats, typically we use some standard octaves. So for those standard octaves, there are some preferred frequencies, and those are written down here. So those frequencies are 1 to 2, that is an octave. So we start with 1, we go to 2, then 4, then 8, then 16, and then we don't go to 32, but rather we go to 31.5, and then double of that is again 63, then double of that is 126, but we go to 125 because we want to end up at 1000. So there's slight variation in the choice of frequencies, then the 63 to 125, 250, 500 and 1000. So that is how we have a preferred set of frequencies, and typically we use these frequencies when we are reporting data on logarithmic scales. And then there is also something known as a 1/3 octave band. So in case of 1/3 octave band, the ratio of F2 to F1 is not 2, but 2 to the power of 1 over 3, which is 1.26. And in that case, the 1/3 octave frequencies are again tabulated here, and they start with 1.25, 1.25, 1.6, and so on and so forth. So these are the octave bands which we talk about. Then we have bandwidth. And what is a bandwidth? It's the difference between upper and lower frequencies in a contiguous set of frequencies. So you have F1 to F2, so that your band is F2 minus F1. Each band has a center frequency, and then the audio bandwidth is 20 to 20,000 hertz. And a lot of times we use these three terms: bass, middle, and high or treble, and they allude to whether the frequency we are discussing about is low frequency, middle frequency, or high frequency. Another term which we will come across frequently will be wave number, which is nothing but 2 pi over lambda, where lambda is the wavelength of the sound wave. And since lambda equals c over f, where c is the velocity of sound and f is the frequency, so wave number is 2 pi f over c, or omega, which is angular frequency divided by velocity of sound. We have already talked about tones and noise, tones, but then there's another type of sound which is frequently used in engineering literature, and it is known as noise. And what is noise? It is essentially a sound which has all sorts of frequencies mixed up into it. And a lot of times we actually define what is the content of each frequency when we are defining noise. So we can have different types of noise. We can have a type of noise known as white noise. And in white noise, what we have is that we have equal power within a fixed bandwidth for any center frequency. So, and then there's another type of noise known as pink noise. And here the power spectral density is inversely proportional to the frequency, or alternatively, you can also say that there was equal power in each octave. And we'll see. This is also known as 1 over f noise, and we'll see some more details about it. So here's a table which talks about pink noise and white noise. So the pink column is corresponding to pink noise, and the white gray column corresponds to white noise. So now let's look at this table carefully. So what you see is that when you have this pink power, so from 1 to 2 hertz band, the total power in that band is 0.75 hertz for pink noise. Then 2 to 4 hertz, again it's a 1 octave wide band. The power is still 0.75. So each time you go up an octave, the band, the total power in that particular band remains at 0.75 hertz. But when you have white noise, then it doesn't happen like that. You start with 0.7, then you go to the next band, your power actually goes up by a factor of 2, so it's 1.5. Then you go to the next octave, 4 to 8 hertz, your power goes to 3. Then you go to 8 to 16 hertz, again that's an octave, but your power, it keeps on going up by a factor of 2. So what that means is that in pink noise, you have per octave the energy content is same, but in white noise you have per octave the energy content keeps on going up as you go up on the frequency scale. And what I will do here is actually play both these types of noise so that you can get a feel of how they sound like. So this is what white noise sounds like. I'll play it again. So this is white noise. And this is pink noise. So this is how these two different types of noises sound like. You can interpret this in a way that pink noise is a little more gentle. It's and if you look at its spectrum, we will talk about this later also. It's closer to real music, but white noise is a little more harsher and not that pleasing or appealing to our ears. So that, I think, brings to the closure of this module, this particular lecture, and thank you very much for listening to it, and look forward to seeing you tomorrow.